So welcome back to another video. In this one, we're going to be talking about the improved Euler method. In the last one, we saw just the regular Euler method. We saw how straightforward it was, how accurate it could be, but even then, it still has some sort of errors. But this one, using the improved Euler, it's basically a little more precise. And this one, it has two equations that we need to use for every single step that we want to find. So you can see the equation for the x, it's pretty much the same than the previous video, right? It's just the previous x plus the step size. And then for finding the y's, we have two equations. We have one in blue, which we call the predictor, and then one in yellow, which we call the corrector. So for this one, basically we have that the first one, we have yn plus 1 star. This is our predictor. And if you see the equations, this is just Euler method. So if for the improved Euler, you first just do the Euler method. All right. And this one will tell us around what values our y should be. This is our predictor. So it's still going to be pretty close. And then doing it again, but with the other formula, we're going to get just a slightly corrected value, just about the same magnitude. So your predictor basically will tell you more or less what your y should be. So if just treat it as if we're doing just regular Euler, and then just do an extra step, and then you actually get the improved. So once again, it's pretty straightforward. It's not difficult. If you have any questions about how to do this one, there should be a link to the Euler method here on top. All right, so for the example that we have here, we have that y prime is equals to y minus y squared. We have initial conditions that y of 0 equals to 0.2, and our step size it's 0.1. Right, so from initial conditions, we get that x of 0, it's 0, and y of 0, it's 0.2. Right, so x of 0, y 0, it's 0, 0.2. So doing step 1, we're going to find our first x. So x1 is equals to x0 plus h, which is just 0.1. And then our predictor, doing first, we're going to find that y1 star is equals to y0 plus our step size times the function of x0, y0. So substituting that f of x, we're going to get that it is equals to y0 plus h times y0 minus y0 squared. If you still have questions, once again, this f of x is just whatever our y prime is equals to. So if we have an x or y, we're just going to substitute those values in. All right, so for this one, it's y0, and then we're going to basically plug in the values. So for y0, we have 0.2, step size is 0.1, and then we have times 0.2 minus 0.2 squared. Right, once you get these values, just put in the calculator, you should end up with 0.216. So if we were to stop here, we will basically just be doing the Euler method again. But we're not going to stop. We're going to do an extra equation in the same step. So see what is our corrected value. And one thing to notice is that the predictor, you can see we got 0.216. So it should be pretty close to our corrector. Like if something changes, it's just maybe a couple decimals are added or just slightly changes, but the overall magnitude should be the same. So if you get a different number in your corrector from your predictor, then you probably did something wrong in your calculations. So make sure that they are pretty close to each other, and you'll see it right now. All right, so let's do our corrector, and you will see that our corrector, it's a function of the previous x and the current x and the previous y and the current y, right? So we have the y1 star. So our actual y1, you can see, it's equals to y0 plus our step size divided by 2 times, you can see we have our function when it was for the previous step plus the function in this current step. So we have y0 minus y0 squared plus y1 star minus y1 star squared, which we just found out right now. So we plug in those numbers, we get y0 over here, and I think there's a typo in this one, right? This one should be over here 0.2, right? This should be 0.2. The value we're gonna get, it's still correct. I think I just did a typo here. The value here should be 0.2 and then plus 0.1 over 2 times 0.2 minus 0.2 squared right? Because those are y naughts, plus, and we have 0.216 minus 0.216 squared. So the value that we get here, it's, you can see 0.2164672. And this value is correct. I just had a typo when I wrote it here. So I will fix this value. Maybe you can see it. Maybe I'm just covering it with like something once I'm editing this video, but just know that this value at the beginning, this should be 8.2, but our end value, it is indeed correct. Right? So you can see how close they are, right? We have our predictor to be 0.216, and now our value over here, it's 0.2164672. So once again, it's just slightly more accurate. It has more decimals, but it is more correct, right? That's what this method is talking about. So let's do another step in this one, right? And here is basically our steps and coordinates. So let's do step 2, and plug it in here. We get that x2 is just 0.2. Our predictor, once again, it's just gonna be y2 star, it's y1 plus h times f of x1 y1, which is y1 plus h times h1 minus h1 squared. And this is 0.2164672, right, out of the number, times everything. And once you plug it in the calculator, this should be equals to 0.2334. So once again, if we stop here, this is just Euler, but we want the improved Euler, so we'll do the corrector. So our y2 is equals to y1 plus the step size divided by 2 times y1 minus y1 squared plus y2 star minus y2 star squared. And this one I do have it correct, right? And this one, it is correct. We do have the correct y1 at the beginning, which is 0.2164672 plus the step size divided by 2 times the y1s plus the y2s, right? So this one, it is correct. The previous one, once again, was a typo. And once we plug in, our answer for this one is 0.23389. So once again, look how close it was. We have 0.2334, and now we have 0.23389. So once again, the magnitude should be about the same, right? If you get two completely different numbers, let's say you got 2.334 and then we got 2.5, well, that's like too far off. So then there's an error in calculations. But these are the correct values, and then plugging it in coordinate form, we get x2, y2, which is just 0.2, 0.23389. So this is basically our results through this differential equation. And of course, you will do this in the calculator or in the computer, in MATLAB, something like that. And you can basically iterate as many steps as you want until your error gets too big or something. And then you just continue this method and stop and just graph whatever you get. All right, so this was the improved Euler method. Once again, it's very straightforward. You gotta do the predictor, you gotta do after your corrector, make sure that they're pretty similar values, and you can do as many steps as you want. So at least for this one, this is this problem. Let's just do one more and regarding improved Euler, and then we'll see you in a different video. But let's focus on this one. So this time we have y prime is equals to x plus 3y. Initial conditions, it's y of 0 equals 1, and h is equals to 0.1. So let's just do one step for this one, because the next video, we're going to compare it to this one. We're going to compare the next video to this improved Euler. So for improved Euler, for this one, we have that x of 0 equals 0 and y of 0 equals 1. But once again, initial conditions, we get, or at x0, y0, we get 0, 1. For a one step only, we get that x1 is equals to x0 plus h, which is just 0 plus 0.1 is equals to 0.1. Doing a predictor, it's as if we were just doing the Euler. So we're going to compare the Euler method to the improved Euler here, right? So we get y1 star is equals to y0 plus h times f of 0, y0. So in this case, we get y0 plus h times x0 plus 3y0. Right, that is our function. So just plugging in the numbers, we get 1 plus 0.1 times 0 plus 3. And if you do the math here, you can see that it's 3 times 0.1, that's just 0.3, and our answer should be 1.3. So through the Euler method, our answer would just be 1.3. Now let's do the improved Euler, right? Which is just doing the corrector part. And then we can see the difference between the two. But once again, we know that our value has to be somewhere around 1.3. So in the corrector, we have y1 is equals to y0 plus h over 2 times x0 plus 3y0 plus parentheses x1 plus 3 times y1 star. So plugging in the values, we see that we're going to get, for the first parenthesis, just 3, right? And here I have, once again, typos. It should be plus. So I'll just fix that one. You should be seeing like maybe like a linear line being added right now. So this should be plus. So we have 3. And then the second one, I have 0.1 times, plus 3 times 1.3, which will make it a 3.9 plus 0.1, that's a 4. 4 plus 3, that's 7. 7 times 0.1, that's 0.7. Divided by 2, that's 0.35. So our answer here is 1.35. So once again, compare the Euler, in this case the predictor part, to the improved Euler, and you can see the difference. We went from 1.3 to 1.35, right? They're still around the same magnitude. We're just adding more decimals. So this is basically how you can start saying which method is more accurate. You can see, at least in this step, that the improved Euler is more accurate than the regular Euler. And in a different video, we're going to be covering the backwards Euler method, and which is a different method, right? And we'll see how accurate that one is as well. So that's it for this video. Once again, this method is pretty straightforward. It's nothing too difficult. There's no algebra so far, calculus, anything. So this should be pretty straightforward for everybody to do. All right, that's it. I will see you guys in the next video.